And what a great way to start off today. We have Srini Devadas, who perhaps you might not know as well. I'm not sure he would call himself a cryptographer.
No, definitely not.
But you are.
But my daughter is trying to be one.
She's trying very successfully, I'll say. So Srini's a little bit from outside the field. And I think he'll give a really, really interesting perspective on some things that we should know more about and we don't. So today he'll be talking about efficient modular arithmetic using vectorization and how it can help speed up cryptographic primitives.
Right. All right, awesome. Thanks, Alette, for that nice introduction. And thanks to Sanjam and Mike and Alette for I should say, acquiescing to my self-invitation, which was, can I come? And they were very nice about it and accommodated this talk, which I hope you will like. As far as I'm concerned, modular arithmetic underlies crypto. Now I understand that there's number-theoretic crypto and all many different kinds of crypto, but if you think about the classical crypto, you think about RSA and Diffie-Hellman, obviously we need modular multiplication and reduction. So this is kind of a happenstance project in the sense that if you asked me 6 months ago, would I be giving this talk? No way. I mean, I didn't know very much about modular multiplication, but Simon Langowski is someone who has a math degree and worked on modular arithmetic as an undergraduate, and is interested in computer architecture as well. So it sort of came together thanks to Simon. The goal is simple: AB mod P, and P is a large prime, and we'd like to speed this up, right? So the goal is what we call strong scaling in computer architecture, which is a term you may not have heard. But there's strong scaling and weak scaling, as you can imagine. But it really comes down to let's reduce the latency, right? So I know lots of people work on batching and amortization. So that's not strong scaling, because you need more than one operation, if you will, and this is really about, the only thing better than this would be improving the clock speed of your processor, because everything gets faster, right? You got this one operation, it's an add, it's a multiply, it's in this case a modular multiplication with reduction. We want to speed the latency of that up, constant time. I mean, this is not something that maybe 30 years ago people would even put on this slide, but now with all of this, the side channels and the smart cards, RSA on smart cards breaking, of course, that's an old break, but continues. We don't want the specifics of the optimizations to depend on the numbers. They can depend on the word size, which is going to be set to t, right? But they shouldn't depend on the exact numbers. So the other thing that's important to keep in mind is that we're really talking about a unit that's not a bit, but it's a word, okay? And the word is 32 bits on GPUs and 64 bits on CPUs, right? So it's actually fairly big. I mean, 64 is a big number, right? So when you think about things like, this will come up, and you might you'll be thinking about this as I talk about multiplication. You think about these subquadratic algorithms and so on and so forth. You got to be a little bit careful here, because the fact is that a 32-bit add is the same cost as a 32-bit multiply. Right? Now, I don't know if that sounds scary to you, but sadly, well, be scared. But it is what it is. With 64 bits, it's kind of the same. But so this whole notion that you're going to replace multiplies with adds and make out like a bandit isn't really true. I mean, it's kind of true, but not true in the sense of the asymptotics that people seem to put out. Okay. The way that people do modular arithmetic these days is division is very expensive, right? And so you do Barrett or Montgomery multiplication that are kind of duals of each other. I'm only going to talk about Montgomery today, obviously this is used everywhere. And the big idea here is that you do approximate division by approximating the quotient, And you try to, whenever you have to do division, you try to make it shifts, because shifts are easy, division is hard, by using this value R. So Montgomery form is essentially something that multiplies by this number R, right? And just in terms of the background before we get into vectorization or the particular algorithm that I want to talk to you about, which isn't our invention, but we've tried to improve it. The Montgomery form is this the R inverse. So the idea is that if you know R inverse, and R inverse is easy to compute, and you compute it once, and you put it aside, then you can do these things, which I won't really explain to you. You don't really need to understand the details, and this is a high-level talk. But you can do these things, and it all works, and this is what people use, right? So Montgomery the multiplication is probably more used than Barrett multiplication, but there's combinations that are used also in use today. So a couple more things. I'm not going to tell you about CRT, so you all know about it. So that's where it's at. And here's the interesting thing from a standpoint of work that a lot of people have done, including myself, in accelerating FHE and accelerating complicated protocols, where CRT and NTTs and having composite moduli corresponding to single word moduli has been central to designing, if not actually fabricating, hardware that can speed up cryptography enormously. Right? So CRT has been the engine that allows parallelism and vectorization, and they're two different things, and I'll disambiguate them in just a second. And so RNS CRT, I mean, it's synonyms as far as I'm concerned, has been central to this. Right? So the difference between parallelism and vectorization is simply put, vectorization is what's called SIMD, which is single input multiple data. So it's the same instruction that is running, so let's say multiply or add or whatever, and it's a little bit easier to build than arbitrary parallelism, because it's the same instruction goes into all of these functional units, and it's different data streams. Multiple data means different data streams, and you end up getting different results, of course. So the numbers are different, but you work with arrays, or you work with vectors, right? That's why it's called vectorization. And parallelism is multi-core parallelism. I'll give you examples of commodity hardware and the two different kinds of parallelism in a few minutes. But that's kind of where things are at with respect to independent add and a multiply run in parallel. That's parallelism. Two adders running in parallel doing exactly the same kind of addition is vectorization. Okay? So mostly we are exploiting vectorization. So to a first approximation, we're exploiting vectorization. So this is a paper that I feel should be more renowned than it is. So 1995. Well, sorry, I'm jumping ahead. So CRT, as I said, was incredibly important for acceleration. All right, but a prime is atomic, right? A prime is atomic. So can you pretend somehow, using clever algorithmics, that prime P is composite and then apply CRT, right? Apply RNS. And amazingly, the answer is yes. And this was a paper 30 years ago, right? So Henry had this beautiful talk on 30 years of PIR, and everyone's at the party and applauding. Well, there's 30 years of Porsche and Porsche, and only two people at the birthday party are me and Simon. Okay, so it's pretty sad, right? But hey, at least someone showed up, right? So here you got 1995, and I'll tell you about a few things that have happened since 1995. Not that many. It's a beautiful algorithm. It turns out you can choose two different RNS bases, and they're M and N, and they have to be 8P and 6P in our scheme, but whatever, right? And the thing is that these are now obviously as large as they have T words, right? But the difference is that the T words are one-word primes. I mean, the T one-word primes, right? And then you multiply them out, and you get this composite modulus. Right? So each base will have one-word primes. And you can select these primes beforehand. Right? It turns out it's not, Mersenne primes or pseudo-Mersenne doesn't really help here because, as I said, a 64-bit multiply is one cycle, right? So at that point, it's like you pick whatever, pick them to be as large as possible. So that would be pseudo-Mersenne. But you can pick beforehand, and that's what we do. T, it turns out you need 2T, but 2T one-word primes, right? 2 raised to W minus whatever, and then you go check it, and you do it once, and you're done, all right? But so now you're working with these composite moduli that are as large as the prime, bigger than the prime, but they're vectorizable, okay? And there's been a bunch of work, by the way. I mean, I'm telling you about things that I haven't done, or other people have done, and I'll tell you about sort of the increment corresponding to what we did as we go along here, right? So all of this is,
sorry,
yeah.
You said, I can't parse the English. What do you mean it will have a T one-word prime modular?
Oh, sorry, that's a typo. That's a typo. So each base will have
yeah, okay.
will have. So let me give you concrete numbers, Shafi. I think this is just a little easier. But so you wanted the original prime was 1024 bits.
Yeah.
Okay. So now you and if the word is 64 bits, then you got it's T equals 16. Mm-hmm. Okay. Now what you do is you choose 16 smaller primes that are close to 64 bits.
Okay.
Right? And there are a bunch of them. Mm-hmm. And you just need 16 of them.
And you multiply them together.
And you multiply them together to get n.
So these are, will have factors. Got it.
Yes,
okay.
yes.
Divisors,
Yeah.
whatever. Okay.
Thanks. Yeah. So that's the story. Generally, the top-level algorithm hasn't really changed, and it was due to Posh in 1995. Like I said, though, there've been some improvements in the representation of numbers and tricks in terms of minimizing the number of multiplies and so on. But you have these two different RNS systems, or two different residue number systems, M and N, and you start with one of them. And I'm not going to give you the details or the proofs as to why this works, but I mean, this has been built and works and there's proofs of correctness as well, not just empirical correctness. And so you actually switch between these two bases, and you end up doing these operations in order to get the result corresponding to AB mod P, which is what you wanted. Okay, so again, the details aren't particularly important because I want to tell you about the complexity of these things with respect to multiplication, and then show you what happens if you go use vectorization. That's kind of the big takeaway from this talk. In that vein, you can ignore pretty much everything else in this little pseudocode and focus on change RNS base, right? So this is now very clean and easy to describe, which is I give you a number in RNS M. I need you to convert it in parallel as fast as possible to RNS N. Okay? And so CRNS is basically the workhorse of all algorithms that are related to this Posh and Posh, and there's been 30 years of work. It's an amorphous community in the sense that we had to dig around and we find the hardware guys building ASICs or claiming they're building ASICs, and then the FPGA guys doing stuff, and the architects and so on and so forth. And so there's been an interesting collection of people who worked on this and made improvements. And in some cases, the improvements didn't last. In some cases, they did. Okay. So change RNS base or CRNS is the workhorse. So if we can speed this up, then we're basically 90% of the computation, or maybe more. Asymptotically, CRNS is where it's at, right? It's T square, and everything else is order T. That's the way to think about it, right? So we want to speed that up. And so I just give you a little sense of what's going on here, okay? And sorry for the fonts, but I decided to do this yesterday, and you can see the results. But so the first thing that happens is so we have M, which is 13, 15, and 19. And so this is T equals 3, and the primes are small, and N is 11, 14, and 17, which is a different RNS base. I have 2076. which I'm showing you the decimal things so you know what they actually are, but obviously there's a representation in RNS corresponding to 965, and then we want to convert that to what is that going to be in n, right? And we want to do that as fast as possible in parallel, okay? And so you need to do some pre-computation. There's a bunch of pre-computation. I will say that the amount of storage that you need in what we call RNS Montgomery, so RNS with Montgomery, we're calling RNS Montgomery, is more than Montgomery, right? Because there's some pre-computation and you need to store these things. So that ends up being an issue when you look at concrete numbers. So you have to do the ICRT theorem factors, but this is a one-time thing, which are 3420, 3211, and 780 for the RNS-M for each of those factors. So you compute those beforehand. And what you're trying to do, the first step of this is actually to estimate K, right? So what you want 2076 equals that, and what is the K for that? And obviously you're not going to be doing division and so on. And it turns out there's this thing called a fixed point approximation, and there's many ways of doing this, which is to compute 93, which is this 3420 divided by M, so the M here is yeah, that's this what is going on here? Yeah, so you got basically this is 93 is, I mean, this is 0.93. That's the way to think about it, because this is pretty similar to that. And this is 0.87. This is 0.22. So that's just set in decimal, and which is why you divide by 100 here, and you get 14, and voila, it turns out that this is actually the correct equation. Okay, so 14 is what you get over there. So the first thing to do, and this is a little bit of, it feels magical, but it does work. And so the first thing you do is get this number 14. And then you go through a bunch of things, and this is where the vectorization comes in, where you represent 3420 in RNS-N, and you represent 3211 in RNS-N, and these are the numbers here. Do a bunch of additions, and you're all doing all of these things in SIMD vector operations, and that's just an aside. And you go through all of this, and you get 843, which is 2076 in RNS-N, right? I mean, I don't expect you to believe me, but it does work. And there's many different variants. And the important thing is that we have our workhorse here, and most of what you see here, you can run it with vector instructions on a CPU or vector instructions on a GPU. So that's kind of the big takeaway. Okay. So that is CRNS. That's what we wanted to speed up, and the rest of it is you could do. There's some parallelism there as well, and you can exploit that. So this is a kind of 30 years of work in this field, summarized on one slide. Just the image from our paper, and that's the Posh and Posh algorithm. This is an algorithm by Kawamura. This is an algorithm by Bahard. So this is like 1995, 2000, 2015, and Opmont is Simon's algorithm. And what I want you to take away from this is, a couple of small points. The representation is changing. So I only talked about Montgomery form, but there's redundant form. Redundant form essentially says you could be, you might have to subtract p. If it's a redundancy of 2, you might get a number, you might have to subtract p from it. Or it might be a redundancy of 3. And then there's also double Montgomery form, which is r square. And so people have played around with lots of different representations, quadratic residuosity, particular kinds of primes. We don't exploit that. That's not on this slide. And so there's been a bunch of optimizations. We just, I just showed you what I think the highlights are from in terms of getting to our algorithm. We conjecture that the number of multiplications, element-wise multiplications in our algorithm is optimal. And you can kind of see from the two things. The CRNS is being used to approximate the quotient and eventually get the quotient, and then also the remainder. So there's a CRNS here and a CRNS here. And Simon's contribution in this slide is a unified notation. So if you read these papers, you would not see this, right? I mean, and a couple of them, maybe not these, are incomprehensible. But what Simon did was look at CRNS in a slightly more general fashion, where you do before you apply CRNS, you do a pre-multiply, which is really what is up here. So you're multiplying by the pre-multiplication, and a post-multiply, right? So you have pre and post-multiply for CRNS. And the nice thing with that is that now you can start looking at these papers, and most of them anyway, and you can sort of put them in this notation, okay? And that's been helpful just in terms of differentiating our work from others, and we're still struggling with that. And the other thing that you want to take away from this is that, I mean, roughly speaking, I know this is, you guys are theoreticians, but the complexity metric of characters, okay, you know, it's getting a little better, right? You know, it's getting a little better, right? You know, so concrete efficiency, characters, okay? And so, yeah, so it turns out, I mean, I can give you better numbers than that with respect to the number of multiplies. I won't tell you what all of these are, but I'll tell you what the final number of element-wise multiplies is down at the bottom. And the final algorithm that I'll show you results for is this one, okay? But the main takeaway from this slide is Simon's a pretty smart kid, okay? That's the main takeaway. So this is the computational cost. And as you can see here, as I mentioned before, you know, CRNS is really where it's at. Those are the only two t-squared terms, right? And so you end up getting 2t squared plus 16t for this opt-mont algorithm that Simon has implemented and proven correct. And it's worse. If you did standard Montgomery, it would be 2 squared plus 2t. And so the game here is, this is more parallelizable and vectorizable than that, right? That's the game. Right? So it's not asymptotic. I mean, we get worse, but we claim we're better. That's a pretty good deal, right? Yeah. Yeah. So I want to tell you about stuff we've built. So this is real. You can download the code. And there's 3 things I want to tell you about. Tell you about a little bit about our GPU implementation. A little bit about the CPU implementation, where this thing, I don't know if you've heard of this, but it's a VX. I don't know what A stands for, but V and X stand for vector extensions. So this is CPUs that you can go, and you know, like AWS has AVX CPUs, so you know, I guess you could ask Yuval for AWS credits, right? You know, or whoever else that's out here. That's what we did, right? I mean, well, I paid for it, but you know, I'm good with taking AWS credits from anyone, you know, and especially you all. But yeah, so you can run it. You have to buy this machine, and it's more expensive, but you can rent it too, right? And so these are things that are out there, commodity. So I call them, we call these commodity hardware. This is like custom hardware is in the future, not as far as in the future as quantum computers, but you know, near future, okay? My lifetime future, okay? So let me tell you about GPUs, and I don't know how much you know about them, but you know, they're massive, and they're also super expensive. So a GPU in each vector core has 128 physical threads, and it's a little bit strange, but you can have 256 virtual threads, which means that virtualization means that you only have 128 adders or whatever, and but you can time multiplex. And that's a single vector core. And there's usually 100 vector cores on a GPU, okay? 92 in this one that we used. So massive. And there's also tensor cores, which are basically systolic arrays and matrix multiply. And I want to get back to that a little bit later. But that's what we got, right? And so it turns out that we're doing vectorization, as I mentioned. So we're within this vector core exploiting these 128 physical threads, and we're not going across the vector cores, because communicating across the vector cores is 10x, you know, at least 10x slower than communicating inside a vector core, right? So it turns out this 2t squared plus 16t algorithm is very highly parallelizable and vectorizable. And so if you had t plus 2 threads, you can get a critical path of 2t plus 2 multiplies. And if you increase the number of threads, you get a critical path of t plus 6 multiplies. And the sad thing about this is that I wish these were bigger, right? You know, because you know, when t, so the numbers I gave Shafi were 16 for t, right, with 64 bits, but GPUs are 32 bits, so it would be 32 for t. And as you can see, you know, 2 times 32 plus 4 is getting pretty close to 128. And so, we'd love to be able to go and do 4t plus 8 and so on and so forth, but we kind of run out of threads, right? And that's actually the reason why we can't run as fast as we could. So, NVIDIA should not be, from my standpoint, NVIDIA shouldn't be doing vector cores, but they'd be mini vector cores. They should be doing larger monolithic vector cores, and then this would be better, right? I'll go tell NVIDIA that, and they'll ignore me. But you do run out of threads, right? So yeah, so I'm not going to explain. I can tell you offline why this thing is so jiggly, but this is measured performance, and you can kind of see that as the number of threads increases, things do get better. We do need to increase the number of threads as the moduli size increases. So this is a fairly large prime, 4096 bits, and then ignore the jiggles. What you're seeing here is this is 2t plus 2, and this is 4t plus 4. And, sorry, this is t plus 2, and this is 2t plus 4 threads. And the number of threads is shown here. So you've virtualized when you get to this point. And I'm going to leave it at this. The only thing I will say is that there is some parallelism even in regular Montgomery that's exploited by NVIDIA's CGBN library. That's not supposed to be very good. So that was good for us, of course. And you get about a factor of 4 at the best case. And I'm sure these numbers will get better. But then, CGBN probably could be optimized as well. Right? Simon's at NVIDIA. And there's some chance that this thing could get put into CGBN. But I'll find out when he gets back. So that's kind of where things are at. So we're limited now by the number of threads in a vector core. Okay. If we had more threads, we could do better. And then really quickly, AVX is, so think of it as a single core and a multi-core processor, but there's a vector unit that has 512-bit registers, right? And so so if you had 64-bit words, then you could have 8-way parallelism. Now it turns out that for the vagary of the vectorization implies that we can't get 8x speed up, even though we can the latency becomes 2x when you do this simultaneous things, just because of the hardware. That's just the way it is. So the maximum speed up would be 4x, and we actually get that. So this is a Flint. So these are things that people use. What do we have here? Flint as C++ baseline, ArcWorks, which is the Rust baseline. This blue thing is the op Montgomery. So after about 500 bits, it gets faster. And then if you look at what happens up until here, we get that 4x improvement after about 1,000 bits or so, right? So that's not so bad. And if that if we actually had 8 simultaneous multiplies, it would be better, like I said. So I have some I could go tell these Intel guys, if they're still in business, that they should do 8x 512 to go to 1024 SIMD and so on. But I want to tell you a little bit about MKHSS.
I ask,
yeah.
You're joking about saying these things, but really, why don't they do?
Yeah. Why don't they do? Because they never had competition and they didn't care. And now they have competition, and well, all of this is being recorded. Okay. All right. Yeah. Well, I didn't say what I said. Okay. Yeah. Yeah. I mean, that's an offline conversation, as you can see. So there's this super cool primitive that came out in Eurocrypt. This is not me. That's the lady at the back there. Okay. And it's multi-key homomorphic secret sharing, which can be used to do a bunch of good stuff. And this is me. Okay. You could say I'm following my daughter around. Okay. I'm not stalking, but following her around. Okay. So it turns out that there's a giant modular exponentiation in this MKHSS protocol that my student, Kevin, he implemented over the summer, and that was his master's thesis, with help from Geoffroy and Sasha, who's one of my former students. And then we submitted this paper, and it turns out you need a 6144-bit prime, and you want to do modular exponentiation with a 6144-bit prime. Okay, so we're like, oh, this is awesome, right? Let's speed this up, right? And so it was an afternoon's worth of work after, not the paper, but after it was an afternoon's worth of work to go grab Simon's library and then run this algorithm that Kevin coded with this RNS Montgomery algorithm. And it turns out, I mean, I'm sad to say that there's a little bit of a memory leak, that we didn't see at 4,000 bits, but showed up at 6,000 bits. But it did speed things up by 2x, and really should be closer to 4x. So this is like performance for free. as far as you guys are concerned, right? Hook up to the library, and your, some of your number-theoretic cryptography is going to speed up by 4x. All right. So so this was nice. And so let me end with, I would say what perhaps would be the most exciting to you folks, right? And it's kind of pretend hardware, right? Usually when things don't exist, they sound more exciting. So the crazy thing is that custom hardware with t-square multipliers can get you an order log t critical path, okay? And so it's just an addition tree of logarithmic depth. And this is what it would look like. Simon and I slapped these slides together, but it's basically t-square multipliers with logarithmic addition trees. And this is the hardware that doesn't exist, but hopefully will exist at least in terms of design and perhaps on a field programmable gate array in a few months. But this is what it would look like. And I just want to leave you with, if you build this hardware, which I think is totally buildable, you could potentially do modular exponentiation in t log t time, right? And so, you got a factor of 4 out of this vectorization. So I feel like I'm reasonably comfortable making the claim that if this hardware was built and deployed, that public key operations would speed up by an order of magnitude, okay? And so, and we haven't, one thing that I briefly mentioned is, it turns out because of the things that I've mentioned about 64-bit multiplies being the same as 64-bit adds, subquadratic multiplication isn't being used in Montgomery even, conventional Montgomery. But when you get to super huge primes, you could argue that maybe it would be helpful. And so we have to explore that. So there's some algorithmic work to do. So yeah, so my closing thought to you is, what if public key operations were as fast as symmetric key operations? All right? So I'll leave it at that. Thanks.
Questions for Srini?
So I guess what your talk makes me think about is not cryptography, but about sort of verifying computations in a way that's cheaper to make.
Yeah.
It's a slight improvement, like multiplication versus division, or doing multiplication, doing operations, modulo, parameterizers, and then verifying.
Yeah.
Have you thought about this direction?
So not in exactly that way, but I think that it's a little bit different in the sense that.
Can you repeat the question?
Oh, sorry. The question was, is there a connection to this to the notion that the fundamental notion that verification is it could be faster than the construction of the result, right? So you can check the result, correctly. And I don't know if that notion is being applied here, Shafi. I'll have to probably think about it a little bit more. But I think
using it, not applying. Not that you are doing it. I'm saying using the fact that you're speeding it up. Speeding up division, speeding up, operations, more large numbers by doing this trick to going to M.
So, I think this approximation, so I think the fixed point approximation probably uses something like that. Yeah, but I'll have to think about it more. All right, thanks. Thank you. Do you want this? Yeah.
All right, let's thank Srini again.
Thanks.
Okay, next up we have Peter Rindle, who will be talking about optimizing pseudorandom correlation generators from LPN.
Great, thank you.